They called it liquid hell. To the sailors who faced it, it wasn't a weapon. It was sorcery. The year is 674. 1,000 ships of the Umayyad Caliphate darken the waters outside Constantinople. The greatest city in Christendom is hours from falling. Then, from the shadows, the Byzantine dromons emerge. What happens next defies nature itself. Water doesn't stop it. Water feeds it. By 674 AD, the Byzantine Empire was the last shield between the Islamic caliphates in Europe. If Constantinople fell, history itself would have been rewritten. But the Byzantines were outnumbered, outsailed, desperate. They needed more than soldiers. They needed a force multiplier. Enter Kallinikos of Heliopolis, a refugee, an architect, a man carrying a secret so dangerous that revealing it was punishable by death. He brought the Byzantines a formula, one that would turn the Mediterranean into their fortress for the next 1,000 years. The exact formula for Greek fire died with the Byzantine Empire, but historians believe it contained quicklime, pine resin, naphtha, and sulfur, ingredients that, when combined, created something unholy. But the real innovation wasn't the chemistry, it was the engineering. This wasn't just oil in a bucket. The Byzantines built a sophisticated weapons system. The liquid was stored in bronze chambers below deck. A furnace heated it to near boiling. Then sailors pumped it under pressure through a bronze siphon, often shaped like a dragon's head. At the tip, a pilot flame ignited the stream mid-air. And here's what made it a nightmare. Greek fire was hydrophobic. Most fires die in water. This one, water made it spread. In 678 AD, after 4 years of siege, Greek fire shattered the Umayyad fleet. Survivors described entire ships consumed in seconds, the sea itself turning to flame. The siege was broken. Constantinople stood. For the next 800 years, Greek fire was the Byzantine Empire's ultimate deterrent. The formula was kept under royal seal, known only to a handful of engineers. To leak it meant execution. To lose it meant the end of an empire. The Byzantines didn't need the largest navy, they just needed this. And for centuries it was enough. But empires fall. And when Constantinople finally collapsed in 1453, the secret of Greek fire died with it. Even today, with all our modern chemistry, we can only guess how they truly did it. The most terrifying weapon of the medieval world remains a mystery. While the Greek fire held the Byzantine coasts, an even more mobile terror was rising from the east. It didn't rely on secret chemicals, but on the perfection of ancient physics. This was the Mongol composite bow. To a European knight, it looked like a toy. To the men who faced it, it was the sniper rifle of the 13th century. Unlike the simple wooden bows of the West, this was a high-tech masterpiece. A sandwich of biological technology that took up to a year to manufacture. At its core was a flexible wooden frame, but the secret lay in its lamination. On the belly of the bow, the side facing the archer, craftsmen glued strips of water buffalo horn, a material that compresses with incredible force. On the back, they layered animal sinew, which stretches like a high-tension rubber band. These layers were bound by a hide glue so strong it required months to cure. The result was a recurve design that, when unstrung, actually snapped forward into a C shape. This pre-stressed the materials, meaning the moment an archer began to pull, they were already tapping into a massive reservoir of stored energy. This allowed a compact 4-foot bow to punch with the same kinetic energy as a massive 6-foot English longbow, all while being small enough to operate from the saddle. But the weapon was only half the story. The other half was the math of the shot. Mongol archers were trained to release their arrows at the float, the split second when all 4 of their horses' hooves were off the ground, ensuring the vibration of the gallop didn't ruin their aim. They used a specialized stone or bone thumb ring, allowing for a snatch-free, lightning-fast release. This turned a line of riders into a human machine gun. Using the Cantabrian circle tactic, waves of riders would cycle in an endless loop, creating a non-stop stream of lead-tipped death from 300 yards away. In an era where most soldiers couldn't see the color of their enemy's eyes, the Mongols were already hitting their hearts. This single piece of engineering allowed an army of just 100,000 to dismantle the Great Wall of China, crush the chivalry of Europe, and forge the largest contiguous land empire in human history. It remained the undisputed king of the battlefield for 500 years, until the smell of sulfur and the sound of gunpowder finally silenced the thrum of the sinew string. But as the Mongols mastered the short bow on horseback, another island nation was perfecting its opposite. A massive 6-foot pillar of yew that would end the age of the knight forever, the English longbow. For 3 centuries, the armored knight was the apex predator of European warfare. Encased in steel, mounted on horseback, they were invincible, until they met the English. At Crécy, at Poitiers, at Agincourt, the longbow transformed the battlefield into a high-velocity kill zone. It proved that a peasant with a piece of wood could kill a nobleman from 200 yards away, and it made the most expensive armor in Europe obsolete. The secret of the longbow wasn't in its size. It was in the wood. English bowyers harvested yew at the precise point where sapwood meets heartwood, nature's own composite material. The dark heartwood at the center, dense, rigid, resists compression. The lighter sapwood on the exterior, flexible, elastic, stretches under tension. When drawn, these 2 layers work in opposition, one pushing, one pulling, creating draw weights that exceeded 150 pounds. This wasn't a weapon you simply pulled. It required total body commitment. The skeletons of archers recovered from the wreck of the Mary Rose tell the story. Permanent bone deformities, enlarged left arms, twisted spines. You didn't just train to shoot a longbow. Your body was rebuilt by it, from childhood. But the bow was only half the equation. The real innovation? The bodkin point. While standard broadheads would flatten against plate armor, the bodkin was designed for kinetic penetration. A narrow, 4-sided spike of hardened steel. When fired from a 150-pound bow, it reached velocities that could pierce 2-millimeter steel plate. It functioned like a modern armor-piercing round in the 14th century. But the true terror wasn't the individual shot. It was the barrage. A line of 5,000 archers could loose up to 50,000 arrows in a single minute. This created a psychological and physical wall of steel. Cavalry charges became mass suicide. The legacy of the longbow is the end of chivalry as a military doctrine. It removed the safety of armor. The knight, once an invulnerable tank, became a target for commoners. This forced a desperate arms race, thicker plate, heavier steel, until the armor itself became a prison. Too heavy to move, too cumbersome to fight in. The longbow bridged the gap between ancient warfare and the industrial killing of the gunpowder age. It established the only metrics that mattered, range and rate of fire. By the time the first muskets appeared, the longbow had already taught the world a grim lesson. The most expensive armor ever forged is useless against a faster, cheaper projectile. But while Europe perfected the science of distance, the East was forging a different kind of perfection. Next, Damascus steel. As the longbow dismantled the armored knight in the West, a different kind of terror was encountered by crusaders in the Levant. They brought back stories of blades that possessed almost supernatural properties. Swords that could slice through a falling silk scarf, or shatter a European iron broadsword in a single strike without losing their edge. These were the Damascus steel blades. To the medieval mind, these weapons were forged with magic. They were recognizable by their swirling, watery patterns, known as the damask. But while the legend focused on the aesthetics, the reality was a breakthrough in materials science that was nearly a millennium ahead of its time. These blades represented the pinnacle of pre-industrial metallurgy, a secret so closely guarded that when the source of the ore ran dry, the technology vanished from human knowledge for centuries. The lethality of Damascus steel didn't begin in a forge in Syria, but in the iron mines of southern India and Sri Lanka. This was Wootz steel. It was a high-carbon crucible steel created by melting iron with charcoal and specific plant fibers in a sealed environment. Modern electron microscopy has revealed the impossible. These medieval blades contained carbon nanotubes and cementite nanowires. These are microscopic structures that provide extreme hardness while maintaining flexibility. By incorporating these fibers, the smiths were unintentionally practicing nanotechnology. This molecular structure allowed the blade to be honed to an edge only a few atoms thick, while the internal matrix of the steel prevented the edge from chipping or the blade from snapping under the heavy impact of combat. Forging a Damascus blade was an exercise in precision. It wasn't just about heat, it was about the thermal cycling of the metal. The smiths had to keep the steel within a very narrow temperature range. Too hot, and the carbon nanotubes would dissolve. Too cool, and the metal would crack. The distinctive wavy pattern wasn't just decorative. It was a map of the metal's internal strength. It was the result of a complex process of folding and hammering that distributed the carbon evenly throughout the blade. This created a micro-saw effect at the edge. Even as the blade wore down through use, the different hardness levels of the steel layers ensured that the edge remained serrated at a microscopic level. It was a self-sharpening weapon that became more dangerous the more it was used in blood and bone. The tragedy of Damascus steel is its disappearance. By the mid-18th century, the specific chemical signature of the Wootz ore was exhausted. Without the trace elements like vanadium and tungsten found in the original Indian mines, the recipe no longer worked. The secret was lost. In combat, these blades changed the nature of the duel. A soldier with a Damascus saber didn't have to rely on a crushing, heavy blow. They could utilize a draw cut, a slicing motion that utilized the microscopic serrations to bypass leather and light mail armor. It was a weapon of surgical efficiency in an age of blunt force. Today we can replicate the look of Damascus through pattern welding, but the original molecular strength of the 12th century blades remains a ghost of history. A reminder that sometimes the most dangerous technology is the one we forget how to build. The age of the craftsman was over. As the secret of Damascus steel faded into history, combat shifted from the skill of the individual to the output of the factory. In 1884, Hiram Maxim invented the first fully automatic weapon in history. It replaced hand-cranked mechanisms with a system that used the cartridge's own recoil to power its cycle. This was no longer a tool of warfare in the traditional sense. It was a harvesting machine for human life. It moved the battlefield away from courage and toward a grim calculation. Rounds per minute. It ended the era of the infantry charge. Forever. The technical efficiency of the Maxim gun relied on short recoil operation. When a round was fired, the explosive energy pushed the barrel and bolt backward together. This motion unlocked the bolt, ejected the spent casing, and chambered a fresh round from the fabric belt. Unlike previous weapons that required manual cycling, the Maxim would continue to fire as long as the trigger was depressed and the ammunition held out. 600 rounds per minute, 10 rounds every second. But this rate of fire generated immense thermal energy. Without cooling, the barrel would warp, melt, or explode. Maxim's solution: encase the barrel in a heavy steel jacket filled with 7 pints of water. This water cooling system allowed the gun to fire for thousands of rounds without stopping, provided the crew could find a steady supply of liquid. In the desperate conditions of the trenches when water ran dry, crews used their own urine to keep the gun operational. It was a weapon designed for endurance, sustained, relentless output that manual rifles could never match. The deployment of the Maxim gun changed the geometry of the battlefield. It introduced the concept of grazing fire and interlocking fields of fire. Because the gun was mounted on a stable tripod, it could be locked onto a precise line. Soldiers no longer aimed at individuals. They created a wall of lead at waist height. In the crossing of a single field, a pair of machine guns could create a zone where survival was statistically impossible. During the opening stages of World War I, this mechanical efficiency resulted in unprecedented casualties. At the Battle of the Somme, the British Army suffered nearly 60,000 casualties in a single day. Many of them cut down by the disciplined automated fire of German MG-08s, the German variant of Maxim's design. The gun didn't just win battles, it froze them. It forced millions of men into the ground to escape the reach of its fire. The legacy of the Maxim gun is the dehumanization of combat. It removed the face of the enemy and replaced it with a rhythmic industrial process. It proved that in the modern age, a small crew of 3 men could hold off an entire regiment. This imbalance of power fueled the colonial expansions of the late 19th century and dictated the stalemate of the Western Front. It was the predecessor to every modern automatic weapon used today. But even as the Maxim gun turned the earth into a graveyard of lead, a new, more apocalyptic force was being theorized in the physics labs of the 20th century. A weapon that would not just fire bullets, but would dismantle the very atoms of the world. Next, the atomic bomb. The machine gun automated the delivery of lead. But by 1945, humanity had discovered something far more efficient. Why fire projectiles when you could split the atom itself? While the Maxim gun was the product of mechanical engineering, the atomic bomb was born from theoretical physics. The Manhattan Project represented the first time humanity harnessed fundamental forces of the universe for total destruction. This was not a tool for tactical engagement on a front line. It was a strategic instrument designed to erase an entire city in a single second. Its development marked the end of traditional warfare and ushered in an era where the primary goal of a weapon was to be so destructive that its mere existence changed the nature of global politics. The era of the soldier was briefly overshadowed by the era of the physicist. The lethality of the atomic bomb is rooted in the process of nuclear fission. In the little boy device dropped on Hiroshima, a conventional explosive charge fired a subcritical cylinder of uranium-235 into a stationary uranium target. This created a supercritical mass, triggering a runaway chain reaction. When the nucleus of a uranium atom is struck by a neutron, it splits, releasing a massive amount of binding energy and more neutrons, which in turn split billions of other atoms in a fraction of a second. This geometric progression occurs in nanoseconds. The heat generated at the point of detonation reaches tens of millions of degrees, hotter than the core of the sun. This creates a thermal flash that vaporizes organic matter instantly within a 1-kilometer radius. Following the flash, a supersonic pressure wave expands outward, leveling reinforced concrete structures with a force that conventional chemical explosives cannot replicate. Unlike the machine gun, which required a crew and sustained fire to control an area, the atomic bomb achieved total destruction through a single instantaneous event. The destructive capacity of a nuclear weapon extends far beyond the initial thermal and pressure waves. It introduced a new, invisible lethality, ionizing radiation. The explosion lofts massive amounts of dust and debris into the atmosphere, which becomes contaminated with radioactive isotopes like strontium-90 and cesium-137. This fallout eventually descends back to Earth, poisoning the soil, water, and atmosphere. Some isotopes remain lethal for decades. On a biological level, high-energy particles strip electrons from atoms within human cells, shattering DNA strands. This causes acute radiation syndrome, internal hemorrhaging, systemic organ failure, and long-term carcinogenic effects. In Hiroshima and Nagasaki, the majority of the estimated 200,000 deaths occurred not just from the blast, but from the systemic collapse of the victims' bodies in the days, months, and years that followed. The weapon did not just destroy physical structures. It compromised the very biological viability of the target area for generations to come. The legacy of the atomic bomb is the doctrine of mutually assured destruction. Its existence changed the definition of a dangerous weapon from something used to win a war to something used to prevent one. The world moved into the Cold War, a period where the possession of these devices dictated every facet of global diplomacy. It proved that technological progress had reached a point where humanity could engineer its own extinction. But even as the world stepped back from the brink of nuclear conflict, the lessons learned in the labs of the 1940s began to trickle back down into more conventional, portable forms of lethality. As the age of the superpower standoff matured, the focus returned to the individual fighter and a simple, rugged rifle that would become the most prolific killer in modern history. Next, the AK-47. While the atomic bomb dictated the grand strategy of superpowers, the actual reality of 20th century combat was decided by something far simpler. A weapon that didn't require a physicist, just a fighter. As the Cold War intensified, the need for high-tech complexity was replaced by a demand for something rugged, cheap, and easily operated by untrained conscripts. This was the AK-47, designed by Mikhail Kalashnikov in the aftermath of World War II. It prioritized reliability over precision. It did not require specialized maintenance or industrial support once it left the factory. Its emergence marked a shift in global conflict, where the most dangerous weapon was no longer the one that was most advanced, but the one that was most available. The lethality of the AK-47 is a direct result of its loose tolerances. Most high-precision rifles are built with tight internal clearances to improve accuracy. But these same clearances make them prone to jamming when exposed to mud, sand, or carbon buildup. The AK-47 was engineered with wide gaps between its moving parts. It utilizes a long-stroke gas piston system. When a round is fired, propellant gases are bled off the barrel to push a heavy bolt carrier group backward. This massive amount of energy ensures that even if the gun is filled with debris, the mechanism will cycle. The receiver is made from stamped sheet metal rather than machined steel, making it lightweight and extremely cheap to manufacture in the millions. It was designed to be handled by a soldier with minimal training, requiring only a few basic movements to strip, clean, and reassemble. Because of its simplicity, the AK-47 became the primary tool of asymmetric warfare. During the Vietnam War and subsequent Cold War proxies, it allowed insurgent forces to maintain high volumes of fire in environments that rendered more sophisticated equipment useless. The weapon uses a 7.62 by 39 mm cartridge, a round balanced between the power of a full-sized rifle and the low recoil of a submachine gun. This allowed for controllable automatic fire. In the hands of millions, the AK-47 became a force multiplier for revolutions and civil wars across Africa, Asia, and Latin America. It did not win through superior ballistics, but through sheer saturation. It is estimated that there are over 100 million Kalashnikov pattern rifles in circulation today, meaning that in almost every conflict zone on the planet, the AK-47 is the baseline for lethality. The legacy of the AK-47 is the democratization of violence. It removed the barrier of entry for modern warfare. No longer did an army need a sophisticated industrial base to remain a threat. They only needed a crate of stamped steel rifles. It has killed more people than the atomic bomb and the Maxim gun combined, simply by virtue of its longevity and ubiquity. It remains the most prolific firearm in history, a testament to the fact that in the theater of war, reliability is often more dangerous than complexity. However, as the 21st century approached, the blunt force of the AK-47 began to be challenged by a new doctrine. One that focused not on the number of bullets fired, but on the mathematical certainty of where they landed. Next, precision-guided missiles. For most of the 20th century, victory was measured by total erasure. Carpet bombing, strategic destruction, the indiscriminate elimination of an enemy's industrial capacity, and everyone within it. But by the late 1960s, the objective changed. It was no longer about how many tons of ordnance could be dropped, but about the surgical removal of a specific target with zero margin for error. This demand led to the development of precision-guided missiles, PGMs. This technology shifted the focus from the mass of the explosive to the sophistication of the sensor. The fog of war, the ancient uncertainty of the battlefield, began to dissipate, replaced by the cold, digital certainty of laser guidance and GPS coordinates. The lethality of a precision-guided weapon is located in its control section. Unlike a traditional gravity bomb, which follows a predictable ballistic arc, a PGM is equipped with adjustable control fins and an internal computer. The seeker head at the nose of the missile acts as its eyes, detecting laser reflections, infrared heat signatures, or high-frequency GPS signals. A forward observer marks the target with a laser. The missile's seeker locks onto the reflected energy, invisible to the human eye but perfectly clear to the sensor. As the missile flies, its internal processor calculates its trajectory hundreds of times per second. If the target moves or the wind shifts, the computer adjusts the fins mid-flight to compensate. This turned the circular error probable, the statistical measure of a weapon's accuracy, from hundreds of meters to less than a single meter. This mechanical accuracy meant that a single strike could now accomplish what previously required hundreds of bombers and thousands of unguided munitions. It fundamentally changed the logistical footprint of modern warfare, making mass less important than information. This precision introduced a new doctrine: surgical warfare. By theoretically minimizing collateral damage, military forces could strike at the heart of an enemy's infrastructure. Command centers, bridge spans, power grids, without the total erasure of the surrounding civilian population. A specific room, a specific vehicle, a specific individual. However, this efficiency created a new kind of detachment. Warfare became a remote, digital experience conducted from climate-controlled rooms thousands of miles away. The dangerous weapon was no longer a rifle in the mud, but a line of code and a stable satellite link. This is the final stage of an evolution that began with the physical strength of the longbow and ended with the digital ghost of the guided strike. The human element has been moved further and further from the point of impact, turning the act of combat into a series of mathematical equations. Throughout this journey, from the hidden fires of Byzantium to the microscopic precision of the modern missile, we see a consistent pattern. These tools are not just instruments of conflict. They are a mirror of human progress and the lengths we go to overcome the limitations of our own biology. From the moment we first shaped a piece of wood to strike from a distance, we have been on a relentless pursuit of efficiency and reach. We study these weapons not to celebrate their impact, but to understand the forces that have dictated the borders of our nations and the course of our history. They are a reminder that while our technology has evolved from wood and sinew to atoms and algorithms, the weight of their consequence remains the same. The history of the weapon is, in many ways, the history of humanity's attempt to master its environment, often at a devastating cost. If you value this objective look at the technology that shaped our world, consider subscribing. It helps us continue to bring these technical histories to light without the filter of myth or glorification. Comment below with the country you're watching from. Understanding our global community helps us refine these stories for the next chapter. Thank you for your time.